Everyone, let's start with a lecture of struct today. So we are finally going to look at structs. You have heard about it a lot till now. Today you are going to get a formal definition of it. Okay, so struct properties. The C struct mechanism is vaguely similar to Java C++ mechanisms. It supports the creation of user-defined data types. Struct types encapsulates data members. Okay, so yeah, but there are vital differences. Struct data members are public. In fact, there is no notion of access control. Okay, so there is nothing like private or like protected. None of them exist in struct. Struct types cannot have function members. Technically they can, but most of the time they cannot. There is no concept of inheritance or of polymorphism. Okay, so the main concepts of class does not exist for struct. It only is kind of similar. That's it. So this is how the syntax looks like. Struct location. This is the struct identifier. This is the name of the struct. These are the members. Okay, and remember this semicolon is very important. If you do not put it, you are going to get segmentation fault. Not segmentation fault, you are going to get syntax error. So this is a basic struct example. You can download it in the GitHub link that is given. So we are declaring a struct location, and it has two members, X and Y. So remember I was talking about like during struct you need to declare them as global. Okay, you cannot declare them as local, but if you want to have them like be accessed throughout the program, you should declare them globally. Okay, so that is very important thing to note. So anyway, int main. So if you're doing this struct location, you have to write struct location and then the instance name, variable name. Okay, and you can access them directly, a dot x, a dot y, just like class. Okay, assignment is supported for struct types. Type declaration syntax used here requires specific use of struct in instance declaration. Okay, so whenever you want to declare an instance, you have to make sure you write struct location. One way to avoid that is to use typedef. Okay, so another struct example is we are writing it this way, and don't worry about this underscore. Is just a convention. You do not have to put it if you don't want to. But then the next line is going to be typedef struct location and then the new name of the type. So now you can just use them directly. You don't have to write struct over here. Okay, use typedef. Use of typedef creates an alias for the struct type, simplifies the declaration of instances. So this is definitely more preferred than writing struct every time. This is another one which I personally prefer. It's a shorthand, and it, like, honestly, if you get used to it, you wouldn't even be using this. So you can write the whole thing in one line, which is typedef struct location. You don't even have to put it if you don't want to, but you should as a convention, and then you name the new one. Okay, so it is basically combining these lines into this. Okay, then you can just directly use this. It is up to you whichever version you prefer. You will probably see this one the most, but I prefer this one. Struct limitation. What else is supported naturally for struct types? Well, not much. Automatic support. No automatic support for equality comparison or other other relational comparisons. No automatic support for IO of struct variables. No automatic support for deep copy. No automatic support for arithmetic operation, even if it makes sense. Can pass struct variables as parameters. Default in pass by copy, of course. So it is call by value, not call by reference. If you want to do call by reference, you have to send the pointer. Can return a struct variable from a function. Can implement other operations via user-defined non-member functions. Okay, so it won't have any member functions unlike class. So struct has many limitations. The biggest use of it is to encapsulate multiple variables into one. So here is a struct function example. So we have this. So we are going to create a function that initializes it. Okay, so it takes in a struct pointer and it has x and y. You can do this or you can do this. Most of the time you will see this usage. I also prefer this personally, so whichever you use is up to you. And most of the time if you see any sort of like C example, you will see this notation. So if there is any type of struct pointer, you can use this. If it is not a struct pointer, if it was not here, it would be l.x. Okay, so things to note here is must pass location object by pointer so the function can modify the original copy. Because if you just send the structure and like directly the variable and not the address, it will be a call by value. So whatever changes you make in the function will not reflect wherever it is being called from. Given a pointer to a struct variable, we can access its member by dereferencing the pointer to get its target and then using the member selector operator dot. The parenthesis around this like star L is necessary because this has lower precedence than dot. Okay, however you can write L pointer x instead of pointer L dot x. Use of address of ampersand operator in call to create pointer A. Never mind. Sorry. So what we meant over here is we have a local variable called A. We are using ampersand to send the address. Okay, just a standard address call by address call. Another struct example, we have another function which is update location. We can actually send the older structure and a newer structure, sorry, wherever it is being moved to, and then we create a structure in the function, and then we send it as a return address, sorry, return. Okay, so in this case the return type is going to be location. So we do not allocate updated dynamically. There is no need, since we know that at compile time how many we need, and we can just return a copy and avoid the cost of dynamic allocation at runtime. So in this case there is absolutely no reason for malloc or calloc or whatever. So many times you will feel like you need to do malloc or you need to do calloc for structure or whatever you are trying to return. But most of the time it's best to avoid that. Like in this case you do not need it. You know that you are just going to return one structure, so you can just set it as the return type and you just can return the structure instead of doing a malloc. You're free to do malloc, but it is not necessary. And most of the time if you do too many mallocs, sometimes you will get segmentation fault and you will have no idea why that happened. So if it is possible to avoid, it is best if you do not do dynamic allocation if it is not necessary. In C, dynamic allocation should only be used when logically necessary. Okay, like for example, you need a variable length of array. In that case, yes, dynamic allocation is definitely necessary. But if you do not need an array like that, you just need a array that does like certain stuff. In that case, why bother? But remember, whenever you want to return an address, you should be doing dynamic allocation, because a local variable's address will be lost after the scope ends. Okay, so these are some stuff you have to keep in your head, and you learn from mistakes. So you will be making that mistake and then you will be learning. So yeah, don't feel bad if it's not making sense already. Eventually it will. So yeah, you can put all of them in a like header file. In that case, we do the if and if so that they are not declared twice. So this is one way to do it. You have already seen that in the previous lectures. And just to like recap, we do not want duplicate like duplicate declaration of functions or duplicate declaration of structure. So we put if and def, and we put a name, and right after that we define it. So next time it's being defined again, it will check that it is already defined, so this part will not be compiled. Okay, so you will not face an error like duplicate allocation, duplicate declaration. So you can also have arrays as members. Like you can actually have anything as members of structures. Okay, even though you cannot assign one array to another, you can, and you cannot return an array from a function, you can do both of those things with a struct variable that contains an array. Why do you think that's the case? Try to think, try to run it by yourself, and then if you still don't have answer to that, you can ask me, because like if I don't give you anything to think about and I'm just like feeding you everything, then you won't be learning. So yeah, try to think why it works for the struct and does not work for a normal array, and then I'll explain to you. So let's take a look at a struct example, rational numbers. One shortcoming in C is the lack of type to represent rational numbers. A rational number is a ratio of two integers where the denominator is not allowed to be zero. Rational numbers are important because we cannot represent many such fractions exactly in the decimal format. The struct mechanism in C allows us to implement a type that accurately represents the rational numbers within the restrictions imposed by the limited range of integer types. The following slides are a case study based on a course project, which will not be in the sum in this semester, but maybe in some other semester, who knows. Designing data representation. One fact is clear enough: a rational value consists of two integer values. The obvious C approach would be we create a structure called rational. We have the top and the bottom. Okay, we define it like this. A forward-looking approach might use int64 instead, buying in buying increased range and doubling the storage cost. Okay, another thought would be to normalize the representation by using uint32t for the denominator, so that a negative rational number would be always use the negative numerator. Okay, for this example we will stick with the C code above. We will just stick with an integer and not a uint. When implementing a data type, we must consider what operations would be expected or useful for two potential users. In this case, we have the mathematics as a guide. So the basic idea is whenever you are writing a member function in a class, you also have to figure out what type of functions it should need, right? So that is same for C as well. So we will be creating a rational object with a valid value, adding two rational objects to yield a third rational object, subtracting two rational objects to yield a third rational object, multiplying two rational objects to yield a third rational object, dividing two rational objects to yield a third rational object, taking the absolute value of a rational object yielding a second rational object, negating rational object yielding a second rational object, comparing two rational objects with equals, less than, etc. So these are the operations that are available for rational object. We won't be going through all of them. We are just going to take a look at one or two of them. Okay, and of course there are floor and ceiling options. So let's take a look at how we are going to write the add. Okay, so we are sending the left and right. So basically like something like this, left, right. We want to do something like this. So we are sending this as left. We are sending this as right. First, we are going to do a malloc. Okay, you do not have to do malloc, but it's up to you whether you want to do or not. If you do malloc, you should be returning a address, so there should be a star as a return type. If you do not do malloc, which is completely fine, in that case you do not need the star over here. Okay, then we are doing the calculation over here to figure out our value of this new rational uh, number, and then we are going to normalize it. okay, and then we are returning whatever we malloced. Okay, this is how the call is going to be. Give it a try yourself. The code is given in the GitHub. You can also use like send the parameter. Like instead of returning the variable, you can just send it as a parameter, but of course it has to be a pointer of that variable, and then you send them as two variables, because we know that these values are not going to change, and we make changes to them directly. As you can see, this is a pointer, so we are using the arrow notation, okay, pointer notation basically. And then we do a normalization, and then we don't have to return it because it is being sent as a parameter. Okay, so as you can see from here, you are actually returning it indirectly, right? So in the previous lecture, I said that in job interviews, you will be asked like, how can you return multiple stuff using C? So this is another answer. You can use pointers, or you can use structure. In this structure, you know that over here, you know that this structure has two values, right? One of them is top and the other one is bottom. So technically you are actually returning multiple numbers using structure. So this is your answer. Like if they ever ask you, how can you return multiple stuff using C, like in function in C, you just say that you can use either pointers or structures, okay? So we are going to take a look at another example of structures. We know that our array in C doesn't have any like, you know, a parameter of, not parameter, a member like size. So usually you have to send the size as a parameter, right? But in this case, we can create an array data type which has a pointer, which is going to be our array, and it will have the dimension, and it will have usage like the index, like where the index is right now. To initialize it, we are going to do dynamic allocation. In this case, dynamic allocation is important because we cannot say how much size we need beforehand. Okay, we set the size of it. So from next time, we do not have the send the size as a parameter, and we set the index to 0. Then if we want to do a append operation, we can just send the element we want to append. As you can see, we are not using any size over here because this PA holds the size of it. Okay, then we can just make use of it. And in this case, we are doing an append, so it's going to be appended at the last element. And after we put that element over there, we just do usage plus plus. And in this part, it is making sure that if dimension is equal to usage, it is going to return false. So it means that if the dimension, if the usage is like, usage basically means the index, if the index is at the end of the array, then it's going to stop. Okay, we can write another append with more error checking. Over here, we're checking whether it is going past that, or if it does, we can actually add more to it. And of course, we have to do realloc. Okay, by doing realloc, we are basically changing the size. So yeah, so you know that in array there is no deep copy. Like if you write something like two arrays, you have like int a and int b. If you try to do a equals b, you know that it's not going to copy it. You have to write a loop for it. So that is same for pointers as well. Even though the pointers are like, even in case of pointers, you have to write a loop to do that. So let's take a look at iArray copy, where we do a deep copy instead of a shallow copy. Okay, so at first we are doing a calloc. We are checking whether the calloc failed or not. Then we are doing a malloc of the dimension, and then we are doing a memory copy. Okay, they are going to be copied one by one, and then we set the dimension and usage as well. So all this codes are given in the GitHub. Take a look at them, try to run it by yourself, and like play around with it, because struct itself is a very easy concept. It is more of a primitive version of the class. And yeah, I honestly don't know what else to say about struct. So yeah, if you have any questions, let me know. I will try my best to answer those, and I'll see you in the next video.